Dear students, in previous class we already discussed about the density theorem of rational numbers. That is means between any two real numbers there exists a rational number. Now let us discuss about the density theorem of irrational numbers. Means between any two, the theorem states that between any two real numbers there exists an irrational number. There exists an irrational number such that x less than z less than y. So this theorem is immediately followed by density theorem of rational numbers. What is the density theorem of rational numbers? Since x less than y, we have x by root 2 less than y by root 2. Clearly, this x by root 2 and y by root 2 are real numbers. Then by density theorem of rational numbers, there exists a rational number r such that x by root 2 less than r less than y by root 2. That means x less than root 2 into r less than y. So that means x less than z less than y, where z equals root 2 into 1. So this is the density theorem of irrational numbers. Between any two real numbers there exists a rational number. Between any two real numbers there exists an irrational number. This is the density theorem of irrational numbers. Now in previous chapter we already discussed the fact that root 2 is an irrational number. But here we are trying to prove the existence of root 2. Means there exists a real number x such that x square equals 2. There exists a real number x such that x square equals 2. So its proof is done by the following arguments. First we construct a set S. Let S equals set of all S fall in R, set of all real numbers S with the S greater than or equals 0 such that S square less than or equals 2. Not S square less than or equals 2, strict inequality. S square less than 2. We can construct S equals set of all S fall in R with S greater than or equals 0 such that S square less than 2. Then clearly this S is non-empty. Why? Because 0 presents in S. Okay, 0 fall in S, 1 fall in S, etc. 0, 1, etc. are fall in S. Okay. 1 less than 2, 1 square less than 2, 0 square 0 less than 2. So they are all present in S, hence clearly S is non-empty. Let t greater than 2. What about t square? T square greater than 4. Clearly, t square greater than 4 by the choice of S, t is outside of S. T is outside of S. That means S less than or equals to for all S fall in S. S less than or equals to for all S fall in S. So that means 2 be an upper bound of S. S less than or equals to for all S fall in S. By the definition of upper bound, 2 be an upper bound of S. So 2 be an upper bound of S means S is bounded above. S is bounded above. So by the supremum property, supremum of S is X system. Let it be X. Let it be X. Clearly, this X is greater than 1. Since 2 be an upper bound of S, S equals supremum of S equals X, then clearly X greater than 1. Now we have to show that this X square equals 2. We have to show that X square equals 2. By Triptomic property, there are 3 possibilities. Either X square equals 2, or X square greater than 2, or X square less than 2. In order to prove X square equals 2, we have to rule out the other 2 properties, X square greater than 2 and X square less than 2. First suppose that X square less than 2. X square less than 2. X square less than 2 means 2 minus x square is positive. Okay, right. Now consider x plus 1 by n whole square. X plus 1 by n whole square. On expansion, it is x square plus 2x by n plus 1 by n square. Agreed? So means if it is less than or equals x square plus 2x by n plus 1 by y, because for every natural numbers 1 by n square less than or equals 1 by n. Okay, the equality hold when n equals 1. X square plus 2x plus 1 by n means right side is x square plus 2x plus 1 by n. Okay, right. Now again 2 minus x square is positive means 1 by 2 minus x square is also positive. 1 by 2 minus x square is positive. That means 2x plus 1 by 2 minus x square is also positive. Numerator is always positive. So 2x plus 1 by 2 minus x square is positive. By Archimedean property, there exists some n foreign n such that 2x plus 1 by 2 minus x square strictly less than n. That means 2x plus 1 by n strictly less than 2 minus x square. Therefore, x plus 1 by n whole square strictly less than, if you apply the value of 2x plus 1 by n in this equation, so x plus 1 by n whole square strictly less than x square plus, what about 2x plus 1 by n? Less than 2 minus x square. That means x plus 1 by n whole square strictly less than 2. Plus x square cancelling, x plus 1 by n whole square less than 2. X plus 1 by n whole square strictly less than 2 means x plus 1 by n presents in S by the choice of S. S is set of all S foreign R with a square less than 2. So x plus 1 by n whole square less than 2 means x plus 1 by n fallen S. That means x plus 1 by n fallen x means x is not an upper bound. X is not an upper bound of S. That's a contradiction. Hence, this contradiction is due to our wrong assumption. Thus, x square less than 2 is not possible. So, 1 is ruled out. Now, suppose the second case. When x square greater than 2, what happens here? X square greater than 2 means when x square greater than 2. Consider x minus 1 by m whole square. What is x minus 1 by m whole square? On expansion it is x square minus 2x by m plus 1 by m square. Okay. That means x minus 1 by m whole square strictly greater than x square minus 2x by m. Clear? Okay. But x square greater than 2. But let's mark it as equation 1. But x square greater than 2, that means x square minus 2 is positive. X square minus 2 is positive. So 1 by x square minus 2 is positive. That means 2x by x square minus 2 is also positive. Then by Archimedean property, there exists a natural number m such that 2x by x square minus 2 strictly less than m. Okay. Therefore, equation 1 reduces to x minus 1 by m whole square strictly greater than x square minus of 2x by x square minus 2 less than m means we can rearrange it as 2x by m strictly less than x square minus 2. So x square minus of x square minus 2 equals 2. That is x minus 1 by m whole square greater than 2. X minus 1 by m whole square greater than 2 means x minus 1 by m be an upper bound of S. X minus 1 by m be an upper bound of S. That's a contradiction to the choice of x is supreme of S. This contradiction is due to our assumption x square greater than 2. So x square greater than 2 is not possible, which is also we ruled out. So the only possibility is x square equals 2. So this is the existence of x square equals 2. For any real, there exists a real number x such that x square equals 2. Okay, next. Now, consider a problem. Let a greater than 0. Let a greater than 0. As equals a into s. As equals a means a into capital S. As equals small as where s presents in s. Where s fall in s. Now prove that infimum of as equals a into infimum of s. Infimum of as equals a into infimum of s. We already proved. So infimum of a plus s, a plus infimum s, and so on. So here infimum of as equals a into infimum of s. How? So as is given. As equals set of all as for s of all in s. We already know that infimum of s less than or equals s for all s of all in s. Infimum of s less than or equals yes for all s of all in s. Okay. Since a is positive, we know that a into infimum of s less than or equals a is because a is a greater than 0. A into infimum of s less than or equals a is for all a is fall in a is. For all a is fall in a is. Clear? Yes. For any epsilon positive, since a is positive, what about epsilon by a? Epsilon by a is also positive. Then there exists some s not fall in s such that s not less than or equals infimum of s plus epsilon by a. Clear? Infimum of capital S means the set S plus epsilon by a. For any epsilon is positive, epsilon by a is positive, then there exists some s not fall in s such that s not less than or equals infimum of s. Infimum means greatest lower bound. Sure, s not fall in s such that s not less than equals infimum of s plus epsilon by e. That means a into s not less than or equals a into infimum of s plus epsilon. What is as fall in as? So what is as not? That's also fall in. As. So s not fall in s. So a s not also fall in s. So a s not less than or equals a into infimum of s plus epsilon. Epsilon means epsilon being arbitrary. So that means infimum of as less than or equals, since epsilon being arbitrary, it is equals a into infimum s. So this is the crucial point. If as is defined as in this way, then infimum of as equals a into infimum s. Similarly, we can prove that supremum of as, when a is positive, a greater than 0, then supremum of as. Supremum of as equals a into supremum of s. By the same arguments, how we know that we have s less than or equals supremum. Sorry, s less than or equals s supremum of s for all s of all n s. S less than or equals supremum s. Supremum means least upper bound. So s less than or equals supremum of s for all s of all n s. Then that means as less than or equals a into supremum of s for all as fall in as, since a is positive. Okay. Then for all epsilon is positive, for all epsilon positive, then what about epsilon by a? Epsilon by a should be also positive. Then there exists some s dash fall in s such that there exists some s dash fall in s such that s dash, sorry, s not s less than or equals, s greater than or equals, sorry. We have s greater than or equals supremum of s for all s fall in s. As greater than or equals a into supremum of s for all as fall in s. Then for all epsilon positive, epsilon by a is positive. Then there exists s dash fall in s such that s dash greater than or equals supremum of s minus epsilon by a. Okay. Yes. That means a s dash greater than or equals a into supremum of s minus epsilon. A into supremum of s minus epsilon. Since epsilon being arbitrary, we can conclude that supremum of as equals a into supremum of s. Supremum of as equals a into supremum of s. Okay. This is from the definitions of supremum and infimum. We have s greater than or equals supremum s for all s of all in s. Therefore, as greater than or equals a into supremum of s, since a is positive. Epsilon by a is also positive. Then there exists s dash fall in s such that s dash greater than or equals supremum s minus epsilon by a. That is, a s dash greater than or equals a into supremum s minus epsilon. So supremum s equals a into supremum of s. Agreed. So now let x be any non-empty set. Consider another problem. Let x be any non-empty, x is any non-empty set. F and G are defined on S. F and G are defined on X, whose bounded ranges in R. The ranges are bounded in R. Then prove that supremum of f of x plus g of x, supremum f of x plus g of x for all x following x less than or equals supremum f of x plus supremum g of x. Supremum f of x for all x following x plus supremum g of x for all x following x. Supremum f of x plus g of x less than or equals supremum f of x plus supremum g of x. How? For any x following x, we know that f of x less than or equals supremum of f of x for all x following x. F of x less than or equals supremum f of x for all x following x. Similarly, g of x less than or equals supremum of g of x for all x following x. Then, what is f of x plus g of x? So, f of x plus g of x less than or equals, on vertical addition, it is supremum of f of x plus supremum of g of x for all x following x. That means supremum of f of x for all x following x plus supremum of g of x for all x following x be an upper bound of the set. That means supremum of f of x for all x following x plus supremum of g of x for all x following x be an upper bound of f of x plus g of x. So that means supremum of f of x plus g of x less than or equals supremum f of x plus supremum g of x. Similarly, you can show that infimum of f of x plus infimum of g of x less than or equals infimum f of x plus g of x. Okay, the proof is immediately followed from this one. Right.